So the second part of 3.6 has to do with rates of change, which are also kind of the slopes. And there's two rates of change that you need to be familiar with. The first one is the average rate of change. And this happens over a given interval from A to B on the graph. And the average rate of change is just the slope, which is the difference of the y's. So f of b minus f of a over the difference of the corresponding x's. And so this is your average rate of change, and it's represented by a secant line. So if you have a graph that you're trying to find the rate of change between 2 points, and let's say you're looking from this point to this point, if we say that this is the point A with a y-coordinate f of a, and this is the point B with the y-coordinate f of b, then the slope or the average rate of change of this line is going to be the secant that passes through those 2 points. And so like that is your slope of that average rate of change. So the slope of this secant is calculated by using that average rate of change formula. So let's say we take this question here where you're trying to find the average rate of change over this function. Well, if we take that function, we'll go ahead and plug that in here to Desmos exactly as it appears. Oops. So x squared plus 2x minus 3. And if we want to evaluate this, we need to know what the points are here. So we have an input of 3 and we have an input of 5. So let's evaluate each of those. F of 3 gives us 12 and f of 5 gives us 32. So we can now use those values in this calculation. Average rate of change is equal to the difference of the y's, so 32 minus 12, over the difference of the corresponding x's, 5 minus 3. So here we get our answer of 20 over 2, which is 10. So there is the average rate of change within that interval. So you just evaluate the functions, take the difference of their y values, divided by the difference of their corresponding x values. It's just the slope of the line that is a secant passing through those 2 points. Now, compare that to the instantaneous rate of change. The instantaneous rate of change would be a single point on a graph, not the difference between two. And so to find the instantaneous rate of change, what you can do to estimate it in algebra is to use what's called a difference quotient. And you're basically finding the secant of the smallest possible change in x's that you can imagine. So here, instead of it being the secant line, this is going to be the slope of a tangent line. And so you want to get a line as close to tangent as possible. So what we're going to do is we're going to use 2 points that have a very small difference. So now when we evaluate this, we're going to take the difference of two functions, f of x, the point that we're looking at, and some very small change where h is equal to 0.01 is what, 0.1 is what we're going to use to evaluate this. And you can choose a smaller number as well, but here we're just going to use 0.1. That's sort of the accepted version. And so that's all over the actual difference of the x's. And so here the x's are x plus h minus x, and really it's just going to wind up being the h. So what we wind up with here when we're evaluating these is we take the slope of the line between x and f of x. Okay, so that's the point that you're testing. And then the slight change, x plus h and f of x plus h, again where h is equal to 0.1. So using this concept here, we'll take that difference quotient to find our instantaneous rate of change. And so once again, we will evaluate. Let's start with 6. Okay, so if we want to find the change at 6, what we would do is we again begin with our function. F of x is equal to x squared minus 4x minus 9. Okay, and what we want to do is we want to find what is the function at the given point. So here at f of 6, or at an x of 6, our output is 3. And we're going to choose a second point, which is just 0.1 more than that. So if we take f of 6.1 and take a look, how does this change? This is now 3.81. Oops, let's get to that where we can see it. Okay, so here are the two points that we're testing. And so now we find the slope of the line passing between these. So if we take the difference of their y's, so 3.81 minus 3 over the difference of their corresponding x's, 6.1 minus 6. And when you take this calculation, you're going to get 0.81 all over 0.1. Oops. 0.81 all over 0.1. And there is your answer, instantaneous rate of change of 8.1. We're going to do the exact same thing here with 7. So if we test 7, we find the point. And again, we can just come back up here. Let's change this to 7. We get a corresponding y value of 12. And if we take 7.1, we change that just by a tiny little fraction. We get 13.01. And so now when we calculate our instantaneous rate of change here, we take the difference of our y's over the difference of our x's. And when we do that, we get, again, as we perform this, 1.01 divided by 0.1, and that gives us 10.1 for our answers. So there's what we're looking at. We can now compare them. The question is asking us to find which function is changing faster. To see which one is changing faster, you look at the steeper magnitude of the rate of change. So if you're looking for changes faster, it's not actually asking you whether it's getting positive or negative. It's asking basically for the magnitude of that change. So if you take the absolute value of these slopes and compare them, you see that this one is a faster, larger number. As far as the magnitude, the absolute value of that is a larger number. So 7 is going to be have a rate of change that's changing faster. All right. So the final thing, we touched on it in part A, and that is tying in the average rate of change in concavity and reviewing that concept. So when you're looking at a graph, again, that's concave up, so here's our two examples of concave up graphs. Notice here this slope is flat here, but it's getting more and more positive, right? So this is an example of more positive. And in here, we see it's still concave up. Here we have a very steep negative slope, but it's getting less negative. So it's getting flatter and flatter until it becomes, again, this flat graph. This one is getting less negative. So concave up is either a graph that's getting more positive or less negative, and that's considered an increasing rate of change. Notice it's not saying that it's increasing. So here's a case where the graph is increasing. Okay? Here's a case where the graph is decreasing, but in both cases, the rate of change is said to be increasing. It's getting more positive or less negative. Now compare that to the concave down. So these are our two examples of graphs that are concave down. Notice here we have this negative slope, and as you move to the right, it's getting more and more negative. So this slope is changing and becoming more negative. And here we have a steep positive slope. And as we move to the right, that slope's becoming less and less positive. So here's an example where we have a graph that's less positive. Right? And so what you can see here is this is said to be a decreasing rate of change. So AP Pre-Calc students are finding this concept difficult to understand because notice again, it's not asking is the function decreasing, because here the function is decreasing and the rate of change is decreasing, right? It's getting more negative. But here's a case where the function is increasing, but the rate of change is getting less and less positive, which means it is decreasing as well. And that happens when the graph is concave down. So a couple ways that you can see that. So visually you can see it. Concavity is easy to see visually. It's a little bit harder sometimes to see when you are looking at the numbers themselves. So if we look here and we start taking the difference between these functions, okay, so we have, if you look the difference from 89 to 77 here, we get, it's a difference of negative 12, and then we have a difference of negative 15, here a difference of negative 24, here a difference of negative 27, and here the last one a difference of negative 30. So what's happening here is it's getting more and more negative, right? So this is an example of a function that's getting more and more negative as you move up through the x's. So we can see that the numbers here are going down. So this is a decreasing function. So just looking at the y values, we see that the numbers are going down. Oops. So when you look at this, by numbers I mean the y's. So the y's are getting lower as x is getting bigger. So that's a decreasing function. And now as we look at the successive differences, what we see is they're getting more and more negative. More negative, if you look over here, more negative means that this function is concave down. All right, if we look at the next example here, so we see when we look at our functions, we're going from 3 to 7 to 9. So here, if you look at the changes, we're going plus 4, here plus 12, plus 16, plus 20, and finally plus 40. And so what's happening here is our y values are getting bigger as x is getting bigger. So that is a function that increases. And when we look at our successive differences here as we're moving, this is getting more and more positive as we move to the right. So more positive occurs right here, which means our graph is concave up. Now, you could plot these points on Desmos and you'd be able to see how the graph appears. Okay? But you can also just look right at it and you see that once again you have more negative and more positive, and that's going to give you the function's concavity.